Video 7, Chapter 9. What we're going to move on to are some two-sided tests for a two-sided z-test for a proportion. The last video we talked about doing a one-sided z-test, and that was whether our alternate hypothesis was using the less than or greater than sign. Since we're going to be doing a two-sided test, that means we will be using the not equal to sign, because we don't know if we really should be going greater than or less than, so we will consider both. Now, for this video, we're not going to be doing those. We're going to be working on this as what our null and alternate hypothesis should be. We're still going to have the same conditions. We're still going to use the same formula that we did for our calculations of our test statistic. Just keep in mind that our p sub naught value here that we see 3 times in our formula, that value is whatever we have up here in our null hypothesis. We won't be seeing these pictures, but we will rather be seeing this picture. So instead of having one tail, we will be finding the area of both tails. Now, the z that we get here, it could be positive or negative. Okay, if it's negative, then obviously we're going to graph the negative side, but then we'll also consider the absolute value of that negative, and really we'll be also figuring this out. But really we'll just be doubling this lower end to get both ends. Now, if our z statistic, for example, is positive, then we'll go ahead and graph it here where it normally should be, but we'll also mark and shade the negative version down on the left end. Okay, so you still will do both despite this being positive or negative. And then again, we will write our concluding statement, which always refers to the alternate hypothesis in the end. Either we do or we do not have enough evidence to conclude that the alternate hypothesis is true. Now, as I mentioned before, when we don't know which way the alternate value could go, then we will do a two-sided test. So we don't know if our p, our proportion for our population, could be smaller, could be larger than this hypothesized value. Now, one thing you absolutely cannot do is you cannot look at your data from your sample afterwards and then decide which direction to do. Okay, so for example, if you said, I have a fair die and I want to test the notion whether it is a fair die. So I want to focus on rolling a 1. And I think rolling a 1 should be 1 and 6. And if it's not fair, then it should be, something not 1 and 6. So technically we should use the not equal to sign for our alternate hypothesis. Now, if you roll the die, let's say 100 times, and you find out a 1 happens fewer than 1 and 6 times, then you can't go back later and change that not equal to sign in your alternate hypothesis to a less than sign, because that is statistical cheating. So if you don't know which way it's going to go, then you must use the not equal to sign. Another thing to consider here is since we have 2 tails, that means that we will need to double our p-value. Because typically we would be on just say the left end or the right end, but in a not equal to case, we will be on both ends. And since our normal distribution is symmetric, we can just find the area of one of these 2 tails and double it, and there we have our p-value. And then we may compare it to our alpha value. So the example we're going to look at here. It says a coin that is balanced should come up heads half the time in the long run. The French naturalist Count Buffon wanted to test this theory. He tossed a coin 4,040 times, because I guess when you're French and you're in the 7th or the 18th century, you really have nothing better to do than flip a coin over 4,000 times. He got 2,084 heads. Is this evidence that Buffon's coin was not balanced? We're going to perform a significance test at the 5% alpha level. So first, we need to write our null and alternate hypotheses. And our null hypothesis is that the proportion of times that he gets a head, p, should be equal to 0.5. It should be 1/2, should be 50%. Versus we want to see if this coin is unfair, but we don't really know whether we're going to get more or less than 50% of the time or heads. So our alternate will just be not equal to 50%. And P is not the probability, but rather the proportion of times we flip heads. All right, so here's part one. This is stating our hypotheses and defining our parameter of interest. Part two, checking our conditions. Number one, do we have a random sample? Well, can we really call flipping a coin randomly? Well, as long as he was flipping it and he wasn't just like trying to prove a point, trying to get a head or trying to get a tail. This is going to be one of those cases where we will say assume tosses are random, but proceed with caution. So we're going to go ahead and do it because he didn't probably flip these coins in such a way that would produce a biased result, and then we would stop at that point. So we'll just assume that he was really being legit in how he was flipping the coin over 4,000 times. Now, number two condition. Do we have independent observations? So is the population at least 10 times our sample size? Well, our population is really all flips of the coin. And technically there are, so we'll say all flips, is that greater than or equal to 10 times 4,040, which would be 40,400? All flips, there's technically infinitely many flips you could do. So we will say assume true. And if you wanted to, you could say, that we can calculate the standard error, which in this case would be our sigma sub p hat. So there's condition number 2 in check. Now we move on to condition 3. Get the right color, which is, do we have a normal distribution? So we need to check, is n times p naught greater than or equal to 10? And is n times 1 minus p naught greater than or equal to 10? Well, n is our sample size, which is our 4,040 flips, and our p naught, remember, comes from the value that we are hypothesizing, our 50%. And so again, we got 4,040, and then 1 minus 50% is going to give us 50% again, so we're going to end up with the same values here. And half of 4040 is 2020. So both of these cases, yeah, it's true. Boom, boom, check, check. What may we proceed to assume from this point? We may assume we have an approximately normal distribution. So we got part 1 done. We've got part 2 done. Now we need to do some calculations. So I'm going to erase all this. So if you're still writing, you might want to pause the video. Otherwise, I'm going to erase all this so I can get some room. Go back to square one here. So 3, calculations. So here's where I'm going to calculate my z statistic. And I'm going to use my formula, p hat minus p sub naught over square root p sub naught times 1 minus p sub naught all over n. Now keep in mind, all of this fraction here is all underneath the square root in the denominator. Now our p hat, this is what we saw from our sample. And our sample was our 2,084 heads out of the 4040. Now if you want to leave it as this fraction, that's perfectly fine. Or if you just want to round that value, I would personally round it to 4 significant digits, and I get 0.5158. So that is the value I'm going to put in for p hat. Remember, our p sub naught is our hypothesized value, which is just 0.5, over the square root of, again, 0.5 times 1 minus 0.5, all over 40/40. Now, flip you out of the way. Once I put all that into my calculator, I end up with a z-score, 4 significant digits now, 2.014. So this is my z-score. This is my test statistic. And this is what I'm going to use now to help calculate my p-value. So I want to find what is the probability that my z-score, now consider this, my z-score here is positive. So if I have my normal distribution here, my standard normal curve, 2 standard deviations above the mean is, we'll estimate right here. So we'll say this is 2.014. And in this case, we are going to shade this way of it. And since this is a two-sided test, we also need to come down symmetrically to the left side and say here is z equals negative 2.014 and shade to the outside of it. So let's just stick with our 2 value for now. So our p-value by definition is the value that is as extreme as or more extreme than what we saw. Well, the 2.014 is the z-score that we saw. So as extreme as represents the or equal to sign, and the more extreme than represents our greater than sign. So we want to write our probability statement there. And then now we can go use our calculator. And our lower bound is the 2.014. Our upper bound over here is infinity. And so when I punch that in my calculator, I get, and I'm going to do 4 significant digits again, 0.022, and then really 00. So I'm just going to write 0.022. Now this 0.022 represents just the right tail. Now we also have the left tail to consider since this is a two-sided test. So I just need to double this p-value because this end will also end up being 0.022. So my total p-value now will be 0.044. Now, here's where we're going to have to make our decision. Is our p-value less than our alpha value? And it is. So we would decide to reject the null hypothesis. So now let me move this up here and let's write our conclusion at this point. So let me move all this up. Let's get rid of you, throw you in the trash can. Sorry, guy. So now number 4, conclusion. We're going to use our stereotypical statement that we have been using. We do or do not have enough evidence. We're going to say we do have enough evidence. We do have enough evidence at the alpha equals 0.05 level to conclude. And this is where we want to refer to the alternate hypothesis, which was that the proportion of heads is not equal to 50%. So we can either say it that way, to conclude the proportion of flipped heads is not 50%. But what that really means, and this is what you could write instead of that, so you could say to conclude the coin is not fair. It leans more heavily towards heads, just slightly, than it does for tails. Okay, so you could conclude this, or you could write out the proportion of flipped heads is not 50%. And we're officially done with the problem. Now the problem in the book that you can take a look at, and if you want to pause the video, you can kind of look over this. So here is, I believe, part of the answers. Here's our conditions here. Here's our stating part. There's the null and alternate hypotheses. Here's the calculation step. And again, notice down here, as I mentioned in previous videos, they're going to mention using table A, which is the table in the back of your formula sheet, which you don't have to use because I'm always going to use, and thankfully they refer to it here, using normal CDF in the calculator. And if you use normal CDF, you're going to have to draw this picture up here. Okay, so just keep that in mind. Now, one thing I haven't talked about is, what if you use table A instead? What do you have to write to get full credit? Okay, because technically you don't have to draw the picture if you use table A. Table A, you would still have to do this. You still have to write the probability statement and technically what the p-value would be. So you can skip the picture if you use table A, but using table A, in my opinion, is more of a hassle than it is than anything. You're going to spend more time looking up that value in table A than you are just writing out normal CDF and drawing this picture. And last but not least, here's your conclusion to that problem. And here's the one problem that I want you to try and bring it to class tomorrow, and we will go over it together. So again, if you really want to improve your skills on this chapter, I would highly recommend trying this problem out. And you have to do this from beginning to end, which means number one, you need to state your ho and your ha. You need to check your conditions. You need to do the calculations. And you need to write your conclusion. So this is another example of a full out problem here. Okay, so try it out. Good luck, and we'll talk about it in class the next day.